You're back. Okay, so yeah, so this is something that the addition, subtraction, etc. of like fraction has to be very clear. Now, if you pose this problem of, let's say, 3/4 plus 2/5, what is to be done? Then I usually recommend going into that in 3 steps. And there is reason why in 3 steps. Step 1 are problems like this: 1/4 plus 3/8. Now, if you notice, at this level, children need to have adequate exposure to playing with fractions. So they should know that 1/4 can be made with 2/8 or 3/12. Okay. So when they see this, you ask that, and this is where the more you problematize, the better. Okay. So there is 4 and 8. Is there any way we can make? We can't make the 8/4. That part is very clear. But is there any way we can make 1/4 using 1/8? Okay. So deliberately in this first step 1, the two denominators must be factor multiple of each other. Okay. So you can definitely write one of them in terms of the other denominator. And the moment you do that, you are in familiar territory. Okay. And then they should be able to take it forward. Okay. So this is step 1. First type of problems. The second type should be something like, let's say 3/4 plus 2/5. Now, this is where the squares do the best job. Now, this is where what happens is these are co-prime. Okay. So if you use the square, and the fraction square document has details of it, what you do is you take 2 squares to show this. So this is 3/4. Okay. So you got the first fraction. This is 3/4. And then you have 2/5. Okay. Now what you do is, the first one, you divide horizontally into 5 equal strips. Okay. So, and the next one, 2/5, you divide horizontally into 4 equal strips. Now these are to be done on paper, right? So as you rotate one by 90 degree, you realize that the 2 grids are identical. I can't do that here because I can't rotate a picture on the board. But if you draw it out on paper, you can rotate it and see. Okay, so then you realize that now both of them are made with the same unit fraction, right? So the first one is, and you can see it's a 5/3, right? So you can see that there are 5 times 3 pieces, and the total number of pieces that make the whole is 5 times 4. You can see that clearly from the grid. And the next one is, this is 4 times 2, and the total number of pieces, that's 4 times 5. Okay, so this is 15/20 and 8/20. Again in familiar territory now. So all good. Okay, so this is the second one. So the first one is where the denominators are factor multiple of each other. Second one where the denominators are co-prime. Okay. Now, if you are dealing with this with older children, class 8 onwards, then this one method just simply works. You just multiply, and you can see that we have multiplied, divided each fraction by the denominator of the other fraction. This method, if you have to teach one method to a child who is struggling with fraction addition, teach this one. It cuts across. Okay. But when you are teaching a child fraction addition to begin with, you should attempt that the child distinguishes the first case from the second. Because in the first case, you don't need to change both the fraction, you need to change only one. So applying 2 would be an overkill, right? Okay. Now the third case. The third case is where you actually need proper LCM. Okay. Method 2 will work, no doubt about it, but it will give you bigger numbers. Okay. So an example will be, let's say, 1/6 plus 3/4. Okay. Now you notice that they are definitely not multiple factors of each other. Neither are they co-prime. Okay. So this is where you try to think, okay, is there a number which will, is there a unit fraction which can make both 1/6 and 3/4? That's the idea. And they need to get that, okay, so which fractions make 1/6? 1/12 makes, 2 1/12 becomes 1/6, 3 1/18 makes 1/6, 4 1/24 makes 1/6. So they need to have a sense of equivalent fractions at this point, right? So once they have that sense, then you try to figure out, okay, what is that denominator, right? And this is where LCM comes in, and you try to find the LCM of those, or you can simply go look at multiples of each other, meaning numbers which show up in the table. So look at the numbers which show up in the table of 4 and table of 6. If you look at table of 6, 6, 12, 18, okay? If you look at table of 4, 4, 8, 12, okay? So you can see that 12 is there in both. Okay, go for it. And then you basically rewrite this as 2/12 plus 9/12, and you are in your familiar territory. Okay, so 3 levels. At class 6, 7 level, 6 I would say in particular, when you are teaching fraction addition for the first time, deal with each one separately. Spend some time with each one. Okay, and definitely brush up on equivalent fractions before this. Then, if you are teaching this to a child in class 7 and or 8 onwards, then just do 2. Again, depends on the child, but there you probably need to focus on other things, and you need to give the child something to tackle fraction addition. Okay, and if you want to give just one thing, give 2. It works. Okay, so if you try to do 3 with 2, it will be 4/24 plus 18/24, right? And that will give you 22/24. All said and done, whereas the actual answer is 11 by 12. I mean, look at this. 22 by 24 is not incorrect. No way. It's just not reduced. That's all. Okay. So it gets 2 does the job, but it need not give you a reduced answer. That's it. Okay. And that's not a big deal. Okay. So that's about addition, and that kind of leads into LCM also. So I would like to know if you specifically had questions related to LCM, because LCM was also mentioned.
No, not really. Was this?
Okay, okay. But yeah, so if you have, for example, the Jodo fraction kit you have, you can also have fraction strips. And see, Jodo's kit doesn't have 1/5, if I remember correctly, doesn't have 1/9. Okay, so those are also things you can add.
Okay, 2 p.m. Setting your alarm.
Okay, so I mean, in the circle only 1/5 and 1/9 can be easily added. 1/10 also, because these are 5, 9, 10 are all factors of 360 degrees, so it can be done. Very brave souls have tried 1/7. I haven't, because 7 doesn't divide 360 degrees. Okay, and similarly haven't tried 11. Okay, so leaving out 7 and 11, all the numbers up from 2 to 12 divide 360 degree, and so you can, you know, create your own fraction kit or supplement the Jodo kit. You can also try it with strips. Okay, I have found 21 centimeter to be a very good measurement. It's the shorter length of A4 paper, and 21 is beautifully divisible by 3 and 7. And for 2, 4, and 8, you can, you know, halve again and again. You convert 21 centimeter to 210 millimeter, you get 5 and 10. So the only number left out is 9. And you can do a bit of construction. And remind me if you don't have fraction kit, because there is a document called fraction kit, and the construction is given there. It's a mathematically sound construction. So you can definitely do that. At a later point, probably in class 8 or 9, at some point, children learn in geometry, in construction, to divide a line segment, a given line segment, into equal parts. Okay, they learn how to bisect in class 6. Okay, it's one of the basic constructions. But dividing a line segment into 3 equal parts, 5 equal parts, and stuff like that, that is there in class 8 or class 9, somewhere around that. That can be utilized to you know, create fraction strips or that kind of stuff. But there are simpler ways also. And there are nice mathematically solid ways, meaning no approximation, no estimation, etc., on the web. So those can also be utilized. For most practical purposes, 21 centimeter works very nicely. And it's a reasonable length that can be, you know, fit into people's bags and stuff like that. If you want to make a big poster or something, or fraction wall or something, I mean, double it to make it 42 centimeter, etc., etc. You can do all those kinds of stuff. Okay. So yeah. But children need to play with many such things to build up a sense of, to generalize. Okay, to generalize, to figure out, okay, if you are given a fraction p by q in reduced form, let's say, then what will be its equivalent forms? The square model also helps out there very nicely. It can help them imagine how to build other fractions. Let's say we have 1/3. Okay. Now, so 1/3 is our base fraction. Now, if you split it like this, you immediately get 2/6, right? If you do split it further, right, you got 6/18. Similarly, it depends on how you are dividing it, and that basically determines the equivalent fractions. And you can get that this is nothing but, see, 2/6 is nothing but 2 times 1 and 2 times 3. I mean, you split the whole thing into each of these 1/3s, you split into 2 parts, right? So that's where the 2 is coming. That's where the 2 is coming. Similarly, if you split them into 6 parts, okay, this part is getting split into 6, so it became 6 times 1. Similarly, all 3, so it's 6, 6, 6. So that also becomes 6 times 3. So this, this basic idea of multiplying and divide by the same number, that can be learned through the fraction squares very nicely. While getting equivalent fractions, it's often given like, so you want to get 1/3 equal to something over 15, right? This kind of problems are very common. Or let me make it a little bit more complicated. Let's say 2/3 equal to something over 15. Now this is something I learned from community college teaching from some other colleague. It's a good idea to write it with a gap in the middle. Okay. So what you do is, you should know table at this point. Okay. So what do you need to multiply 3 by to get 15? So it will be 3 times 5. So this is step 1. And then if you are multiplying 3 by 5, then you need to multiply 2 by 5 as well. Okay? Because 2/3 times 5, okay. And so this is step 2. And then you calculate how much is 2 by 5, and you get the numerator that you needed, and that's step 3. Now, why you need to multiply both by the same number? That's where the fraction model can help. So you had this. You had your 2/3. Okay. So you need to make it into a fraction which has 15 pieces. So each of these 1/3 need to be split into 5 parts, right? So split. Okay. So now you have total 15 parts, 15 pieces you can see. So that means each of these 2 are also split into 5 each. So earlier, which was 2, is now 5 plus 5, or 2 times 5. So this whole thing can be done. What I really like is, making space and putting this in the middle, because then once you finish, you can see the continuum. Okay. So that's something you can use for equivalent fractions. Nice. Okay, let's see what we have next. And I think today's session will be covered with these more or less. Okay, so the next one is a question from integers. Application of negative times negative. Haha. Now, I don't know if there is a situation in day-to-day life where you need to apply, where you need to multiply a negative number by a negative number. In some science related stuff there may be, but I am not aware of anything like that which is taught to children or which can be exposed to children at class 7. That is roughly the time when they learn negative times negative, right? So it is, in my opinion, kind of futile to try and create a word problem with this. Negative times negative is there because it completes all possible integer multiplication situations. Okay, I mean, there are essentially, if you include commutativity, and why not, because it is a property, then essentially there are three possibilities, right? Positive times positive, there are gazillion examples of that. Positive times negative, that can be figured out. Okay, not too difficult. If you run into loss for 3 consecutive months, what is the total loss? Okay, it can be looked into that way. But negative times negative, I don't know. So I would say don't force it. Okay, it's there for a mathematical reason, and everything cannot and maybe need not be linked to real life. Okay, so that would be my response to application of negative times negative. I'm sure in science you will find stuff, but science that is accessible to children at that level, I don't know. I mean, talk to scientists. Maybe Sanjeev can help. Okay. Now, then there are two very important questions which do not directly connect to upper primary syllabus and borderline connects to secondary syllabus, but they kind of get started here. So let's spend the next half an hour maybe discussing that. Exponentiation, logarithmic function, those are two things. Basically exponential, that's what I would like to discuss. And it is connected to AP and GP. Okay. Luckily for you and me, one of our students did her project on AP-GP. Okay. And you have this chapter on interest, right? Simple interest and compound interest. Think of, and she knows you guys, Gomati, and I have referred what I saw your children do to her and to the class, especially in this context. I remember seeing a scratch project by one child where the child has created bar graphs showing how money grows when it is growing with simple interest versus when it is growing with compound interest. Okay, I mean, that graph was fascinating. It connected so many things and made so much sense. So please take a look at that or create something similar yourself in Scratch. And you will immediately realize that when money grows in simple interest, that's AP, arithmetic progression. And you get a straight line with a positive slope. But when money grows with compound interest, that's a geometric growth, and the curve doesn't have constant slope, it curves up. Okay, and very soon geometric growth becomes explosive. It grows very, very fast. um, so all this talk about GDP and the rate of growth, etc., all of that involves geometric growth. Frankly, I don't know if we really understand it well. And I mean, when Corona came, and okay, anything like infection spreading, etc., follows a model of geometric growth. So, they were, and you probably have seen it, that there were graphs all over the net, and many of the graphs had a regular version and a logarithmic version. Okay, because the regular one grows too fast, and when something grows too fast, how do you make sense of it? So when you convert it into logarithm, it becomes kind of linear, so it becomes easier a bit to handle it. Okay, so exponential growth is something which is not well understood, probably because it comes a bit late into school curriculum, etc. At the same time, anything to do with compound interest naturally involves geometric progression and exponential growth. Think of EMI, okay? And it has a damn complicated formula. But if you want to understand that formula, you cannot escape geometric progression and exponential growth. So when it comes to finance that impact everybody, okay? Monthly saving schemes, okay, monthly income schemes, etc. All of this, anything involving compound interest, has to necessarily deal with geometric growth. Okay, and you cannot tackle that without adequate algebra, without geometric progression. So it's very crucial. There is a talk by an old professor. It's, I think, about an hour-long talk on how common people don't understand arithmetic, meaning exponential growth. He talks about population and energy with respect to exponential growth. I'm going to send you that link. Please see it. Okay. It's kind of eye-opening what he's saying there. Something to do with the doubling time and its implication. And our economic models are based on geometric growth, but until and unless we understand the implication of this doubling time, we better not talk about sustainability and any such thing. Okay, so this geometric growth, etc., are at a very, very important concepts in mathematics, which huge application in various fields. Okay, I mean, economics absolutely for anybody and everybody, and I would definitely say sustainability and stuff. Now, what would be a starting point? In class 6, 7, you start with exponentiation, and you start with 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, etc. And it is very important that they get a sense of that. They get a sense of how large it grows and how fast. One possibility for powers of 2, what you can do is you can do a tree diagram, a branching pattern, and you can use cloth clips. Okay, so if you have cloth clips, it will be like this, and you attach 2 more cloth clips here and here. then here and here, here and here. Okay, and you see how it spreads so fast. Okay, so that's one. And I think after a point, you will kind of, almost run out of space. Observe trees. Okay, there are some trees which are, we have two such trees downstairs, which I call power of three. Whenever it branches into three branches. I mean, three branches, not two, not four, anything, but three branches always. Now you can do that. So I use straws, okay, and I cut the straw into 4 equal parts, and I staple 3 of those parts here at one end, and that's the basic module. And then you can attach another 3 here, another 3 here, another 3 here. The staple, this pin here, that can be used to attach it. And if you have many of this, okay, you grow that tree pattern, grow it on the floor. You can't hold it up and show the whole class. See how fast it grows. So give children a sense of explosive growth, how fast it grows compared to, linear growth. Okay, so that's very important. Similarly, when you, in the next class, okay, let's see. Udavi gets into exponentiation in class 8. Okay, so that's the state board syllabus, as far as I remember. For Easymultiplication, it will be, I'm not remembering whether there is in 6 or whether it starts in 6 or it starts in 7, but it starts in one of these two with positive powers. So, a to the power n, where n is positive. And in the next class, you get to n being all integers. Okay, and so that cannot be modeled with branching diagrams. It can be modeled differently. You basically partition. You can again take the square and you partition it. So this is 2 to the power negative 1, 2 to the power negative 2, 2 to the power negative 3, 2 to the power negative 4, and so on and so forth. And you can see exponential decay, how fast it shrinks. Okay, so for Udavi, both will happen one after the other in class 8. That's according to the state syllabus. But in CBSE, it's split across 2 classes. So that's where you get into exponential function. I mean, not exponential function, but basically playing around with exponents and have a feel for how fast number grows and how fast it decreases. Okay. Now, the exponential function, something that looks like anything of the form a to the x, okay, can be written as e to the bx. Okay, and you can probably put another coefficient in front. So again, lazy bum, right? So if you can figure out e, then you don't need to figure out all those different a's, and you can express everything in terms of e. So that is where the exponential function kind of came up, e to the bx or something in that form. And mathematics tends to grow. Okay, so once you have got exponentiation, so let's look at it this way. Once you can square a number, then you try to think of, okay, what about the other way? And then you come up with square root. So same thing, if you can grow something like this, then you need to want to find the reverse thing. Okay, so let me give you a context from a compound interest situation. Suppose you want your money to double in a certain number of years. Then, see, if you know what is the rate of interest, so you have A equal to P1 plus R T to the N, 1 plus R to the N, or R to the T, right? Now, if you know P, if you know A, and if you know T, you can figure out R, right? But how do you manage to, so you know it will be A by P equal to 1 plus R to the T. Okay. So how do you get rid of the T from that side? Is it too low?
Yeah.
Can you see now?
Yeah, that's
okay. So see, how do you get rid of the T from the RHS? Okay, you need to get to R. Okay, so this is where the root function comes in. Okay, you take the Tth root. So you take the Tth root on both sides, and that takes care of it. Okay, but okay, let's say you have now you have got A equal to P1 plus R to the T, and T is unknown. Okay. So, well, A by P is equal to 1 plus R to the T. How do you isolate the T now? T is unknown. What do you do? So this is the situation when you need logarithm. Okay. So that is where it kind of came up. So when you know T, you want to find R, taking appropriate root does the job. Okay, I'm deliberately not going into is T an integer? Is T obviously, in a money context, T will be positive number, not negative number, right? And definitely not 0. But there are questions like, for example, is T going to be a natural number? Can it be a fraction? So most likely in a money context, it's not going to be a real number. So less complications there. And as long as it's a natural number, you can define what's the root, etc. So all those things. But if R is given and you need to find T, then, well, that's when you need logarithmic function, which is opposite of the exponential function. So that's where the need comes from. Okay. And I'm not sure if exponential and logarithmic functions are there in secondary level. These things